Okay, let us come back to random variables. I think last class was probably a lot of equations with not much explanations, it became fairly monotonous. So let me see if I can add some explanations. Okay, we have been through a bunch of the sort of typical variables, and some extra squiggles are there. All right, so few definitions which I thought I should come back to, right, and then let us see. So first of all, expectation. Of a random variable, right. So that is standard definition. This is all practice, I have to get used to this, writing faster on this one. Okay, there is some particular angle that this I have to this, right. Okay. So if it is a discrete, okay, that worked 3 times before I got that right. No. So if xi is the value of the variable and p of x xi, right. So I is your xi's are the set of all possible values, right. So this you would know, this is your mean basically, right. And if it's yeah, you can also represent that as if it's a continuous random variable, it is simply your summation, right, of all possible values of x into my infinities are looking like alpha, but you know that it is infinity, and this does not always close. So this is your continuous random variable. Okay, there is another little button here which I press, something funny happens. Okay. We will figure all this out, or at least I will figure all of this out. Right? This is continuous, this is discrete, right. And in general I can extend this expectation to any function of the random variable f of x, right. So that is f of x, right, is again the same, it is simply f of applied to xi and then the probability. So this px xi just means that what is the probability that, right, random variable x takes the value xi. We have seen this before, and this is I. That is again definition, sometimes we will use this later on, right, as needed. Then we have this special, right, e of x squared, expectation of a function f applied to the variable x. So in this case x squared is, for example, right, a function. So if f of x is x squared, then e of x squared is defined this way, right. So this is, so I will show you x squared, right, xi squared. We can always go back if you want to, it is not that it is permanently gone. Oh, so it is whatever, it is for each variable you are applying the function f and then multiplying that with the corresponding probability, right. So x squared is a simple example, right, this is x squared for over all I. And what is special about e of x squared? There is another name for that. Variance, no. Second moment, right. So e of x is your first moment, this is your second moment. So later on we will talk about moment generating functions too, right. So this is your second moment. And then your variance is actually defined as, so what we normally write that as variance of x, that is e of x squared minus e of x whole squared, that is variance, right. And then standard deviation is simply square root of e of variance of x. This is following me from home, that ant came with the bag. Okay. There is another definition for variance too, right. Remember the other definition for variance? x minus e of x, right. So it is the expected value of x minus e of x whole square. That is also our definition, right. So, but both are equivalent, you can derive this either now or in tutorial session later, right, as to why this is true. Okay. So that is some things that I wanted to, and then okay, and okay, just write this here. So variance of x is also your standard deviation squared, sigma x squared, right. So when we use sigma or sigma x, that is what we mean. And there is one more parameter or one more metric that one can measure, called the coefficient of variation for a particular random variable. Simply sometimes we call it COV. This thing is not going away. What is the coefficient of variation? Sigma is horrible. Okay. That clear? Okay, I think that's about the basics that we wanted to do first. Up and up. And there is one more metric called the dispersion index, or dispersion, yeah, index of dispersion, VMR. Sometimes we also just use this as index of dispersion. See, I am trying to avoid touching the screen, but apparently that is not feasible. That is simply ratio of variance to the mean, right. So it is called VMR, variance to mean ratio. So this also is called. So VMR is something special, right. So it is either 1 or less than 1, greater than 1. These are the three possible cases. If it is equal to 1, then what variable is it? There is only one variable for which VMR equal to 1.
Poisson.
Discrete Poisson, right. So Poisson variance equals mean. When we look at Poisson again, we will visit that, but that is usually as a test if you want to see whether your measured data. See, normally what we assume is we assume that the distribution is Poisson, do all our assumptions, but it is the other way around all the time. When you do your experiments and you are trying to take some measurements for say service times and many things, then you want to retrofit that to some sort of known distribution, because you want to take that and use that to generate traffic later on, right. So sometimes you do some test measurements traces, and then you want to use that as a way to generate new traffic models, because sometimes when you want to do something mathematically, you should know what the possible distribution type is, right. So anyway, so VMR is one only in the case of Poisson. Okay, so these are some of the essential definitions that I wanted to cover. Okay. So next we will get into, again this is still, we are still in the probability or random variables business. So you heard about moment generation functions? I only see two head shaking. How many of you have heard about moment MGFs? MGF, okay, only 2, 3, 4, 5. Okay, so I will go through that. How about probability generating functions? PGF, okay, it is tied to MGF, that is fine. So you have Laplace transform, right, some of those things you have heard of. Okay. So now let me just, again, this is about part of background, because some of the cases for which we are deriving the mean and variance and so on, I am just giving you the values, but I would like you to try those out also, right. We will do that in the tutorial session. I will just go through some of the highlights of that today. Okay, so we are now in page 3. Okay, I am going to go to page 4. So moment generating function MGF of a random variable x is simply defined as follows, right. I will just use Kishore's definition. So that is summation over all the possible values that this variable x can take. So here is your f of x, right. F of x in this case is simply e power xj theta, but theta is some whatever, we will see what is. Theta can be integer, it cannot be integer also. Okay. And in the case of continuous random variable, correspondingly your summation will go, right, from minus infinity to plus infinity e of x theta f of x dx in case of continuous random. So this m of theta may not exist for all values of for most of the cases that we look at, we can derive this MGF in those cases. Okay. Yeah. Questions? So far definitions only. Okay. So now, so this. So instead of theta, right, if you have some other terms like z or minus s and so on, you end up with different transforms. I will look at only two of them. This can also be your Fourier transform, but since we do not use Fourier transform in the derivations, I will simply leave that. So there are two sub cases or special cases of this MGF, right. So one is if x is a non-negative a continuous random variable. So if x is non-negative and a continuous random variable, then our Laplace transform comes in. Remember, so if I define Lx of s, Laplace transform can be applied to any function, but in this case we are talking about our right. This is the same as applying my instead of theta, I just simply use minus s, right. And because it is continuous, I am going to be using my non-negative. So technically this can be 0. So 0 to infinity is, this is defined as your Laplace transform of this particular random variable. And why this is useful? It can help us easily determine your mean and variance and things like that, right, without having to go through this. If you use the function f of x directly, it is sometimes harder to get to the mean and variance, but using this you can sometimes get the mean and variance quite easily. Okay. So that is your Laplace transform. Got it? Questions? We will look at one example so that this gets clear. So that was for this continuous case. In the case of x being non-negative discrete random variable, then we have its then the Ztransform, sorry, Ztransform, right. So Ztransform, which is we usually use this gx of z, right, is simply now this is by definition your probability generating function. So you would have this as z to the power x, right. So there is some variable z to which you are raising your random variable, right, and this is the same as I did something to it which I should not have done. Make sense? Do I have to explain that? Have you got that? Okay. So E of right z raised to the power x is summation over all I. So this is z to the power xi, right, and then the probability of, this is my definition, right. Remember that I defined E of fx, fx in this case is some variable z to which you are raising it to the power x, right, and depending on the value of z you get different things, right. If z equals 1 you get some things, some terms and so on. So it is simply for every variable, every possible value I simply raise it to the power, raise z to the power that value, right. Now this I can write in terms of my exponent, right. So can I write z in terms of E? So what is z in terms of E? Right, natural log of C, right. So now my summation becomes e power xi into natural log of C.
So Bade, why the non-negativity condition?
Oh, why is the non-negative condition there?
Yeah.
Oh, okay. I'll have to go back and check.
For Laplace transform, it should be non-negative, but for C
but
transform,
discrete also why there? Okay, I've yeah. So okay, but as to why I do not. That's the definition as it's. Okay, so this now looks familiar, right? This is e to the theta, right, into xi, and this is your theta basically, right. So therefore I can make this, therefore this is nothing but mx to the power, so theta becomes lnc, right. So again it's a lot of this is still definitions, it's kind of boring at 2 o'clock in the afternoon, but just bear with it. So then some few properties that we will see where needed. So if y is a variable which is defined as dependent on x, right, with this y equals a plus b, then the moment generation function for y is basically that. Right. right. So a theta, so ax plus b, again this you can go back to derive from basic principles. This is just a property that if needed we will try to use that.
It may sound silly, but why are we doing all these calculations?
Why are we doing? Because when I am talking about the random variables, I need to do some of the basic properties of RVs before I go into exponential and so on. So when I say the exponential is equal to lambda or 1 over lambda and so on, right. So then at least we should know why it is, how that is derived, right. So this is a definition, just bear with this for the next about 20 minutes or so, right. And I don't know, because many times you may want to actually derive when we are doing later performance analysis, for example, right. When you have say several independent traffic sources coming to a multiplexer, right, that is, then you know the independent distributions of all those, but you want to know what the collective distribution is of that variable itself. In those cases then you would, it is, if you know the distribution for the traffic coming to this single queue analytically, then you can use those analytical results, right. So that is why so for example if you know that this each of this next one is that, right. So if I have say x or n different traffic streams coming to this queue, and now we are not looking at simulation like we did last time, right. Now we want to know what is the actual distribution of this particular composite traffic sources. In that case I can use some of these things to derive my corresponding distributions.
Right. What exactly, like I was meaning that once we are writing these down, if like you have just explained, you can just tell, okay, this maybe this is the scenario that we are using.
Okay.
It.
Okay, so yeah, for that I will just come to that example with exponential if you want. Okay, let me stop this properties for just a second, and I will go to your right. Okay, so let us look at this MGF for exponential. So what's the, I used a e power minus ax, which is okay. Some books use lambda e power minus lambda. The textbook actually uses 1 over a e power minus 1 over a, which is sometimes confusing, right, because you have to think that 1 over actually is the mean, a is actually inverse of the mean. So I will just use for now just lambda, right, which is what we used in the case of the Poisson traffic arrivals. Okay, so this is my f of x, right. So lambda is the rate parameter, it is called the rate, right. So when this lambda specifies the so called rate, and the 1 over lambda is the mean of this variable. And always if you look at Raj Jain's book, he does not care, he says x greater than or equal to 0, and Kishore is very particular, says x greater than 0 only. So that is why when I did that lambda yesterday, right, we are trying to plot x equals 0 for exponential. Well, this according to this book you do not really look at x equals 0, only x greater than 0, which in sometimes makes sense if you are looking at inter packet arrival times. You are presuming that 2 packets, it is not going to be, it is at least 0 plus, right, some some epsilon value is there, right, before the next packet can arrive. So anyway, so equal to 0 really does not make a difference, but we will just use this other book definition. Okay, so this is my function, right. So now what is the Laplace transform for this one? You simply replace theta in our equation with minus s, right. So all the double E folks probably have seen this 1000 times, or even I thought we did this in second year math, right. Second year of college math or first year college math, we have derived Laplace transforms left and right for all sorts of complicated functions without knowing why it is used for. So here is one case where we can actually use it, right. So what is it now? It is e power minus s, right, or e power theta x is what we had, theta is minus s, therefore it is e power minus x, and then of course lambda I am going to take the lambda out, and because this is positive we are just okay. Oh, for that, okay, minus. Okay, so then it is lambda, this is basic Okay, so what is the value?
Lambda by
X full integration.
lambda by s plus
Lambda over s plus lambda or lambda plus s. So that's your, this is your MGF. So with this we can generate all the moments that we want, right. So now if I want to find out the mean, I haven't told you how to get the means, right. Yeah. Okay, so E of x, right, can be obtained by simply differentiating with respect to theta and setting theta equals 0 or m dash of 0, whatever how you want to say that, right. So you can generate the moments by simply differentiating this function left and right or continuously. E of x squared is m and so on, right. So this is our definition of the moments, that is why it is called the moment generation function. So now in this particular case E of x equals d of your Laplace transform divided by ds, right, setting s equals 0, and that is nothing but minus lambda by lambda plus s whole squared s equals 0.
minus s of L of minus s.
Yes, yeah.
So it's like lambda by lambda minus s is what the MGF is.
Lambda by lambda
Minus s will be the MGF. We have computed the Laplace transform, so L of s.
Okay, so it will be
of
minus x equals 0. Yeah.
So m of s should be lambda by lambda minus s.
So we computed it of minus s. We computed the
No,
Laplace
no.
respect to
Laplace.
in our definition at least we used minus s as the, so that is why it is lambda by lambda plus s. If I used s, it will be lambda by lambda minus s. But I am using, you're saying that it should be s instead of minus s.
No, what we did was we computed the Laplace transform, and here we are differentiating the same thing with respect to
s. We are only with respect to s only I am differentiating s.
yeah,
And setting s equals 0.
Laplace, not
We have done only Laplace.
MGF.
MGF
Well,
should be.
the MGF is your generalization of the Laplace. So your MGF was e power theta x, right. So in that instead of theta I am using minus s. Okay, so with respect to minus s, not with respect to s.
With respect to theta, which is minus.
Okay, okay. All right, if I respect with minus s, what will I get? Then you, okay, let me go through the computation again to see if actually if I do that. You know what? Okay, let's check that with so with this if I get minus 1 over lambda then I am in trouble, right. I do get that, yeah. Yeah. With respect to a minus. So here it will be, I will be getting minus, yeah. Okay, so this will be minus, yeah. So I will have to okay, I will just make that plus, differentiating with respect to theta, right. So theta is minus s, or we will just say minus of this whole thing. So only this term will change. It is still lambda by lambda plus s is your Laplace. If you differentiate with this, then you will get this negative term out. Yeah, I didn't catch that well. So this is lambda by lambda squared.
Oh, you have put that minus.
Yeah, just put minus. Oh, you actually, yeah, I missed that. Minus 1 to the power k. Okay, yeah, there is actually, I'll go back and write that formula afresh, right. So if you have the Laplace, then your E of xk is minus 1 to the power k d of Lx divided by ds. Now that makes right. Now your minus is always there, because when you go to the second, oh, I cannot do the minus there. So I that out. Oh, at s equals 0. So that is one way of trying to compute the mean first moment, right. I could also have computed the mean another way by simply using the definition itself, right, which we will do in the tutorial. This is one way. So if I want to find out the, so we saw that E of x now is now 1 over lambda, right. So what is E of x squared? 1 by lambda squared, because everything is now, is it 1 by lambda squared? Look again. E of x squared is not 2 by, it's 2 by lambda squared, right. So you have lambda by lambda plus s whole cubes. What is the differential of that? See, we had figured out that dl by ds, right, was lambda minus lambda by whole square, right. This is just your d squared and what is that, 2 by lambda squared. So that is the purpose of using this in some, because minus is now absorbed here. See, this is your right, if this is the definition, so the minus 1 to the power k, right. So when you differentiate lambda by lambda plus s, you would get this one, minus lambda by lambda plus s squared, and because of the fact there is a negative 1 when k was equal to 1, that negative got absorbed, right. But when I go to the second differential, then I get this. So second derivative, I am sorry, yeah, so this is for the kth derivative, yeah. So oh, I forgot the k here, gosh, okay, and k here. That does not look like a k, we will have to adjust that. That does not look any better. And in the case of your Z transform, remember what is E of x. So I used the term G, right, generator, probability generating function. So this is basically D remember that x is in terms of z, right. So differentiate with respect to z and set z equals 1 0 1 whichever. In fact, with this you can also not only get the amounts, you can also get all the probabilities. P of xi also can be obtained, but that we will not look at right now. Okay, and in this one only two E of x and E of x squared is all that is defined, unlike the other one where all the other moments can be obtained. So simply differentiate with respect to z and once twice z equals 1.